Today we're going to go over section 6.1 and 6.1 through 6.4. And really this is going to add context to the integration stuff. To start off with, we're going to talk about integration by parts. And this idea of integration by parts starts with the product rule. We're going to say, all right, let's say we have two functions and we multiply them together. When we take the derivative of those two functions, it turns out to look like this, right? So let's say we're given an integral that looks something like this. We say, I don't know how to integrate this. Well, we can go back to the product rule and say, you know, I do remember that the derivative of these two things multiplied together, just like it says in the slide, is equal to u times dv dx plus v times du dx. Okay, well, how might that help me? Well, notice what we've got is a shared term, right? So let's rearrange this so that we isolate just this one term, yeah? When we do that, we're going to get u dv dx is equal to d dx of u times v plus v times du, or my mistake, minus v times du dx. Well, now we got to integrate both sides, because what we're trying to do is integrate this term, right? So we're going to integrate both sides now. Integrate with respect to x, integrate that whole thing with respect to x. Well, this we can break up, right? Since this is what we're solving for, let's just leave this as it is for right now. Let's rewrite this whole thing. When we rewrite it, we get the integral of d dx of uv integrated with respect to x minus v times du dx integrated with respect to x. Well, this integral, this is just an antiderivative, right? And we're just taking the derivative of this. So they cancel each other out effectively. Agreed? So we can come along here and say, this thing just rewrites to uv minus the integral of v du dx integrated with respect to x. That is equal to our original integral. And this we can rewrite again as uv minus, if we think of these dx's as canceled, that's not what's actually happening, but we can think of it that way, right? Just to abbreviate notation. If we think of it that way, then we can rewrite it as v du. Right? So this is called integration by parts. And what it's saying is that if you want to integrate something like this, you can rewrite it as that. Now, how the hell is that going to be useful? Because it doesn't really seem like it ought to be. Well, it's useful because sometimes cool cancellations might occur. So for example, let's consider this first example right here. we've got the integral of x times ex with respect to x, right? Okay. Now let's for a moment think about this. One of these two functions can be thought of as a u, and one can be thought of as a du, or I mean as a dv. So our possibilities here is to set u equal to x, in which case dv dx would be equal to e to the x, which would give us that dv is equal to e to the x dx. Yeah. Or we could go the other way and say maybe u is equal to e to the x, in which case dv dx would be equal to just x, which then would tell us that dv is equal to x dx. Or we could go with another combination and set u equal to x ex, in which case dv would just be equal to dx, right? That's not particularly helpful in this case. So of these two, which do you think you might want to use here? The right one. Well, all right, let's consider that. If this is the case, then du dx is equal to e to the x, right? Here, we get that v would be equal to 1/2 x squared, right? I don't know that that helps us, because we added a power to x squared, and we still can't integrate that, right? So what I'm saying now is when we put all this back together, I'm going to erase this now. Go ahead and do that. So assuming we use this, we're going to have that u is equal to e to the x, then du dx is equal to e to the x, dv dx, we're arguing is equal to x, in which case v is equal to 1/2 x squared. Now coming down here, du would be equal to e to the x dx, and dv would be equal to 1/2 x squared dx. Okay, so let's go back to what integration by parts looks like. We're saying, if we try this approach, that the integration of x times e to the x with respect to x is equal to u times v. It's going to be e to the x times 1/2 x squared. So that is x squared e to the x over 2 minus the integral v we said is equal to 1/2 x squared, and du is going to be equal to e to the x dx. But we still can't answer this integral, right? We still can't integrate that. So this wasn't the right one. But let's try the other one. Let's see what happens with that now. All right, so let's say that u is equal to x. Then du dx, well, that's equal to 1. du then is just dx. Coming over to the side now, that means dv dx. Well, that's equal to e to the x. But when you integrate that, we're going to ignore the constant right now, because we're just going to tack it on to this term. When we integrate this, it just comes out to be e to the x. So v is equal to e to the x. And dv is equal to e to the x dx. So let's put all that together now. When we put all that together, we start off with x times e to the x dx is equal to, well, u times v is x e to the x minus the integral of v e to the x times du, which in our case was just dx. This I can't solve. This integrates out to be x e to the x minus e to the x plus a constant, right? So this is the power of integration by parts. It lets you say, I don't know how to solve this integral, but I can rewrite it by breaking up my function into the product of other functions. And when I do that, that gives me something I might be able to solve. So as a pro tip, one thing that might be useful here is to start off by looking for u's that reduce in some way, right? So in our case, if u is equal to x, du dx is equal to 1. So if you can reduce the power on an x, it's usually a good approach. Usually, not always. That being said, sometimes you do have to rearrange things in really weird ways, set them equal, and do some other work. But the general setup, the general set of guidelines would be to say, let dv be that hardest part. Then let u be the part that's simple, because when you take the derivative of something simple, you get something simpler more often than not. And that's what they're getting at here. Does that make sense? Folks at home, does that make sense?
Yes.
Awesome. So just looking really quickly at the way they go about this. They consider each possible combination of integrals. You have the case where x is u and dv is e to the x dx. You have the case where u is e to the x and dv is x dx. You have the case where u is 1 and dv is x e to the x dx. And you have the case where u is x e to the x and dv is dx. Well, this is kind of a trivial case that doesn't really help us solve anything, because we still can't find v, right? Finding v here would be the same thing as being able to integrate the original problem. So x that one. Here, maybe, because v now would be x, right? And du dx would be e to the x plus x e to the x, right? And that still ends up giving me something with x e to the x, and I don't know how to solve that. All right, so maybe hold on to that, but let's ignore it for right now. Let's come over here. Well, we just solved why this one didn't work, right? And we saw why this one does work. So they go ahead and say, cool, let's use dv and u as dv equal to e to the x dx, which implies that v is going to be equal to e to the x. And let's let u be equal to x, then du is going to be dx. Because du is du dx times dx, right? So using this setup, now we can go back, identify what our dv, our u, our v, and our du are, plug all those values back into the integration by parts formula, we get our solution. This is the way this generally works. And the reason why we like it is because there are a ton of integrations that we can't solve without it. Just like the one we just saw in the book. Just like the one we just did. You can't solve this problem without integration by parts. And that's the power of it, is it lets you leverage something you know about derivatives, the product world, and say, well, using that, when I integrate this thing, I know something about how that will integrate out once I rearrange my terms. So we're going to leverage that to get something nice. That's what this tool is doing for us. Okay, what about here? I want you all to try this problem. I'm going to give you all about 3 minutes to. And then somebody at home, I want you to tell me what you chose u in dv to be. So 3 minutes, and I'm asking someone at home how to solve this. I think I'm going to do that a lot next semester. Ask people at home. Ask you this question, folks. That way everybody comes to class in person. Uh, 14, 15. In 3 minutes left, yeah. And then look at the clock. Folks at home, what do you think? What is our U? Folks at home, what do we think? Well, right now, let's play with this a little bit. Let's just consider a couple different things. Let's start by considering u to be equal to the ln of x. Let's start there. U is equal to the ln of x, then du is going to be equal to 1 over x dx, right? Or dx over 1 over x. I mean over x. If that's the case, then dv has to be equal to x squared dx. And v would have to be equal to 1/3 x to the third, right? Let's try and put all this together now. We're going to come over here and we're going to say, we've got the integral of x squared ln of x dx. This thing is equal to, well, setting u equal to the ln of x, setting v equal to 1/3 x to the third, you get x to the third over 3. Now we're going to subtract the integral of, well, v, we just said is 1/3 x to the third, and du is going to be dx over x. Or we can rewrite this as 1/x times dx. But notice we get a cancellation here. That's convenient. Let's work with that. This is going to come out to be the ln of x times x to the third, all that multiplied by 1/3, minus the integral of, well, we can bring out that 1/3, so let's go ahead and do that. This x is going to bring our power down by 1, so we're going to have x squared dx. Well, I can integrate that, can I? Question, did I do anything wrong here? Let's flip. Yeah, everything looks good, right? Because we've got, well, looks good up to a point, I should say. What did I do wrong? Oh, no, I didn't. Sorry. I started to say something totally different. Solved a different problem in my head. It happens from time to time. All right, so from here, we know how to solve that, right? We're just going to say, all right, 1/3 x to the third times 1/3 plus c, right? And rewrite all of that as best as we can. And instead of writing it on the board, I'm just going to point to it here. Notice we start off by saying what's u and what's v, or what's dv. We say u is the ln of x, dv is x squared dx. If dv is x squared dx, then v would be the integration of this thing, right? It's going to give us 1/3 x to the third. Cool. And if u is equal to the ln of x, then du is just going to be the derivative of this thing times dx. The derivative of this thing is just 1/x. So multiplying by dx, we get dx over x. Now, an important point should be noted here. This is subtraction, right? Be careful of that. This is where a lot of mistakes happen. It's right there. This is the most common mistake to be made. For example, let's say instead of ln of x, we had 1/x. Then we'd have to inject a negative, right, and change the signs. Things like that, mistakes like that happen all the time with integration by parts. And that's actually where I was looking at it like, I made a mistake. Oh, no, I didn't. I solved a different problem in my head. All right, so now jumping ahead, How might we solve a problem like this? First, what's the integral of the ln of x? Do we know it at all? Is it obvious, maybe? It's not. So what?
Nothing. I was like, I feel like it should be, but
It's not, right? But it feels like you should. It really does feel, at least I thought it felt like it should be when I came across this problem. And on more than one occasion, I have looked at it and been like, what? Well, that's not what I thought it was. Okay, moving on and solving this out by hand. So we're going to solve this by starting with the question of what's u. What do we think u is going to be here? Let's argue that u is going to be 1. If that's the case, then dv is going to be the ln of x dx, right? Does that help us at all? Nah, because we're still going to have to solve that integrand, and this is the integrand we don't know how to solve. So this isn't going to work, and we can see that right away, right? Just because if we set it up this way, we end up with the exact same problem. All right, so let's go the other way. Let's say that u is equal to the ln of x, and dv is just 1 times dx or dx. Okay, well, du then is going to be 1 over x times dx, agreed? 1 over x dx, and v will be the integral of dx, that's just x. So now we're going to come along and say, cool, let's set this problem up and solve it. We've got the integral of the ln of x dx. This is equal to, well, u, we said is the ln of x. V, we found to be x. Minus the integral of, well, again, v is x. And du here is 1 over x dx. And that's convenient because there's a cancellation here now, right? And what we end up with is the ln of x times x minus the integral of dx. So this is all equal to then x ln of x minus x plus a constant. So checking our work, that's exactly what they did, right? They said, cool, let's set dv equal to dx. Well, let's set u equal to the ln of x. Well, that's going to tell us that v is equal to x, and du is equal to 1 over x dx. So when we plug all of these into the integration by parts formula, we get exactly what we just found. So yeah, this integration was not obvious at all. Like, who would have thought you'd get this extra term floating in? Maybe it's understandable to say, all right, we're going to get ln squared of x, maybe something weird like that. Nope, it is x ln of x minus x plus 0.7. All right, so new problem. I flipped the wrong slide. New problem. Now we're going to find the integral of x squared e to the x dx. Well, I want to bring everybody's attention really quick to the point there, to the fact that we just solved a very similar problem, right? This is similar to the integral of x e to the x dx. It's not the same, but it's similar. So reasonably, we might assume that we're going to have a similar setup for this problem, right? If that's the case, then what are we going to set u equal to? Well, if it's going to be similar, shouldn't u be x squared? And then du would be 2x dx, 2x dx. dv would be e to the x dx. And v would be just e to the x. So setting all of this up now, we've got the integral of x squared e to the x dx is equal to u, we just said is x squared, times v is e to the x, minus the integral of, well, v, again, is e to the x, and du is going to be 2x dx. That's a d. We can rewrite all of that. We can rewrite it as x squared e to the x minus 2 times the integral of x e to the x integrated with respect to x. This is why I pointed out the similarity between these. Because now, you know how to solve this. We're going to have to do this again. So since we already know how to solve this, I'm just going to go ahead and jump to the moral of the story. Moral of the story, putting all this together, you're going to have to use integration by parts twice. You're going to have to say, all right, cool, I know what u and I know what dv will be. It means I know what v and u will be. And I can set up that first integration by parts. Well, shit, I don't know how to solve this. That means I'm going to have to set up another integration by parts. Setting that up, you're going to get x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Notice this is one of those cases where that subtraction sign matters, right? Because this integration has its own application of by parts. So we're going to have a minus sign in there, and we're going to have to distribute. Like I said, this negative is where most of the mistakes happen with integration by parts. This is the thing to look out for. Say, all right, this entire thing is equal to its own integration by parts. So all of this is going to be inside of one set of parentheses that has this negative sign applied to it. So once I distribute that, this term is going to become negative and this term is going to become positive. And that's what we're seeing here. That negative, and then it distributes to that, becomes positive. And then they say, hey, notice we can factor out e to the x. So let's go ahead and do that. And if you really wanted, you could check your answer by applying the derivative. Now, what about when we want to apply it to a definite integral? Well, we're going to just say, cool, apply by parts and pull out your bounds. So in the event that we change this a little bit and we say, I want to put bounds on my integral, so I have a definite integral. I want something like this. The integration from a to b of u times dv dx, integrated with respect to x, is equal to, well, apply by parts, and then plugging your bounds. That's the idea here. Makes sense? So you apply the bounds to the whole thing. This is just a really common mistake because it's easy to think, all right, I want to distribute my bounds to this term, but it's to both. Cool. And that's really why I have this example in here to show how this actually is going to work out with the definite integral. So we've just seen the integration of the ln of x. That came out to be x ln of x minus x plus a constant. But since we're using the definite integral, we can drop that constant. It falls out anyhow for the algebra, right? So what do we do with those bounds? Well, we say, cool, I know what that integral is. That's this thing. Now apply those bounds to that thing. Cool. So just a couple observations. Just because it looks like integration by parts does not necessarily mean is integration by parts. This is the only problem of the three where you have to apply integration by parts. This is just the power rule. Because you've got the derivative of the ln of x times the ln of x integrated with respect to x. So this is like u to some power times du dx integrated with respect to x. So it's power rule. This is the log rule. Because we have 1 over u, so 1 over the ln of x times the derivative of the ln of x, 1 over x. So again, integration by parts, right? Both of these are examples of integration by parts. I mean, not integration by parts, of u substitution. I misspoke there. These last two are examples of u substitution. This first one is an example of integration by parts. And we can see how kind of things change, right? One, we get this weird polynomial-esque thing. It's really not a polynomial, but it's polynomial-esque. Here we get this weird thing, and here we get the ln of the ln of x. So just as a heads up, where you will commonly use integration by parts, these two different forms. And usually when you have x to the nth power e to some a times x, so this is a constant a, right? You're going to want to set u equal to x to the n. Whereas in the second example, you're going to want to set ln of x equal to u. So these are just two examples to be aware of, or two common forms to be aware of, right? So n is any power, and a is just a constant. I'm going to skip over that for the sake of time. I'm going to get, no, I'm not. I'm going to really quickly go over 6.2. So section 6.2, I think is actually one of the more intuitive sections in this entire class. It's all about integrating by tables. And what I mean is, you've got a table of integrals. This thing is giant. It's not 1 page. It's not 2 page. It's not 3 page. Oh, it is 3 pages here. Okay. But we've got, in this one table alone, 43 different integrations. Just to give you all an idea of how few this actually is, I have a book, I'm not kidding you, is probably a good 6 inches thick of just integration tables. And it used to be back in the day, before a lot of these were programmed into computers, that mathematicians would have volumes of these books. And I'm really not kidding, 6 inches thick. And every bit the width, or I mean the size otherwise of a textbook. Talking about giant books. And we would keep volumes of these because we don't want to necessarily have to do every type of integral by hand. If it's already been done, don't work harder, work smarter. And that's the idea behind integration tables. To say, all right, I have a really weird integral. Maybe it looks something like 6. I don't want to solve this by hand. I'm going to open up my book of integration tables and figure out what that integration is going to look like. So here I would say, whatever my constant A is, I'll plug that constant into here, and here, and here. Whatever my constant B is, I'm going to plug that into here, here, and here, right? That's how these tables work. You say my integral looks like it's one of these forms. My constants correspond to these different forms. So let's put all of this together now and solve. So let's say we have this example right here. The integral of x over the square root of x minus 1. First thing we're going to want to do, rewrite that, because that's ugly. I don't like that. I'm going to rewrite it as, well, first I'm going to write it down, right? The integral of square root of x minus 1, or the integral of x over the square root of x minus 1, integrated with respect to x. This thing is equal to x, rewriting it using powers now. The quantity, x minus 1, raised to the negative 1/2 power, all integrated with respect to x. All right. Now, I don't like that. It's ugly. I want to do this by hand. Ain't nobody got time for that. But I do have a table of integrations that I might be able to use. So let's go through this table of integrations and see if one jumps out at us that looks kind of like what we're looking at. We go through here and we're like, well, this 19 kind of looks like it. This 20 kind of looks like it. Kind of. And that's, of these, the only ones that kind of look like it, but let's keep looking. None of these fit the bill. None of these really fit the bill. Since our table is so small, we're just going to go ahead and go through all of those, right? And look at each one individually. None of these look like they fit the bill. So it's got to be this 19 right here or this 20, right? So let's see if we can rewrite our integral to look like one of those. We'll start by saying they all use the radical, so we're going to keep the radical. We can rewrite this as the integral of x over the square root of, we need a constant a. So just go ahead and say -1, right? -1 plus, we need a constant b. Let's just go ahead and call it 1. Times x. Integrated with respect to x. Hey, that does in fact fit the bill, doesn't it? We're going to say, cool. A is equal to -1, and B is equal to 1. So according to this, this thing should be equal to negative 2 times the quantity 2, A, which we said was -1, minus V, which we said was 1, times U. Well, I didn't really talk about it just now, but U in this case is going to be X, right? Times X, all divided by 3 times B squared times the square root of A, which was -1, minus B, which was 1, times U, which was X, plus a constant. Now we're going to say, cool, I got some simplifications that can happen in here. Start off with, we've got -2 times the quantity, -2, minus X, divided by, well, 1 squared is 1, so just 3 in our denominator. Come over here, 2, this is going to be -1, minus X, all that raised to the 1/2 power, plus a constant. Now we can simplify this even further by distributing that -2 through to get, this whole thing comes out to be 4 minus or plus 2x divided by 3 times -1 minus x raised to the 1/2 power plus a constant. And that's all there is to it. When working with these integration tables, you just go through, you identify your constants, and you say, cool, based on what I have, based on what my tables tell me, and based on what my constants are, what each of these represent, this is what my answer should be. So now, I zoom back out, and I go to the answer. I say, hey, check it out. Same thing. They just factor out the 2 here, right? Factored out the 2 and distributed the negative sign. Uh-oh, there's a mistake though. Should be x minus 1. What happened there? Well, going back, we say, oh, duh, that was supposed to be plus BU, not minus BU. Okay, that's a simple mistake to fix. Plus, plus, plus. Simple enough mistake to fix. And we can easily check our work looking through this, right? Like I said, this is the idea of integration, of using tables of integrals. It's really not too revolutionary. Let's say, for example, we want to integrate something like this. Well, there's going to be an integration that we can use that is going to be du dx, or I shouldn't say it that way, that is going to say that u squared minus a squared times du looks a particular way. That's what's happening here. So what I'm trying to say is, if we rewrite this as substitution by parts, we're going to get something that looks like this, right? I mean, not by parts. If we use u substitution, we're gonna get this. And once we get this, then we can go through our table and find formula 21. And then we can solve this much more easily. Is this cool with everyone? People at home, is this cool?
Yes.
Awesome. In that case, what do I have next? So something to point out is just that a lot of what happens in tables of integrals is that you'll have one integral turn into something plus another integral. Usually this is a simpler integral, and their point is you can do this by hand on your own now. So as an example of that, formula 36 tells us that the integration of u to the n, e to the u, integrated with respect to u. Well, this thing looks like that. We just did this though, right? And after a couple reductions, we got to our final answer. Now, using this formula 36, we have a lot. We're saying, all right, cool. U here is going to be x. N here is going to be 2. Let's plug this in. Well, what do you know? We get to this. Well, by formula 35, we can rewrite this according to that. So rewriting and expanding and then factoring e to the x out, you get the same answer. So the point here is just to say that sometimes you'll have a thing show up in your integration table that's like, well, thanks, you just gave me another integral, bro. But the reason why is because either there is another integration table you can apply here. There is some sort of a math trick you can apply here. Or it's an integral that you can do by hand very easily, right away. Having said that, I will let y'all out for a quick break. Come back at 7:10.